All right, welcome to Temperature Equipment Corporation's weekly webinar. This week's topic is HVAC codes as related to control systems. Some of you guys were on the webinar last week where we talked about IECC 2015 for both Wisconsin and Illinois. There will be some overlap with this week and last week because obviously some of the things that related to the new energy codes also correlates to control systems. But we'll try not to overlap too much. So today we're only going to focus on commercial control systems, and we're not going to talk about anything else other than that. And about the first half of the stuff we'll talk about today will be IECC related, and maybe the first 15 minutes of that will be overlapped with last week. But everything else beyond that should be new topics that we've not covered recently in any webinars the past year. All right, so moving on. And there's also a question chat box. So if you guys have questions that you want me to answer, go ahead and type them in there, and I'll do my best to answer them. I will likely answer them while you guys are answering the quiz questions on the screen. For you guys that need PDH hours, those quiz questions will pop up. I believe there's 6 of them this week, and you'll need to answer 4 of the 6 correctly in order to get CEUs for Illinois and Wisconsin PEs. So keep that in mind. They're not hard questions. If you're following along, if you're not paying attention, then obviously you'll be guessing. So today we're going to talk about a lot with the energy code as related to Illinois and Wisconsin, and specifically control systems. Talk a little bit about 90.1 as it relates to that. Those two kind of go together, right? IECC and 90.1 are buddies, if you will. We'll talk about the mechanical code and his correlating ash rate standards. Those kind of work together. We'll talk about energy codes and mechanical codes. And we'll also mention a few different pointers and tips as they relate to ash rate standard 55 for thermal comfort, Wisconsin code, Chicago code, ash rate 15 for refrigerant safety, and obviously from a controls perspective, and things like that. We'll touch on a few of those. We're going to stick on the prescriptive compliance paths today. Some of these standards and codes have other compliance paths, such as energy modeling in case of energy codes. We're not talking about any of that today. We'll stick on the prescriptive compliance path. All right, so from an energy code perspective, in Illinois, we've been on the same code for the past 2.5 years. In Wisconsin, we just switched to the 2015 about a month ago, the beginning of May. I'm mainly going to focus on Illinois and Wisconsin because 97% of you guys that registered are from those 2 states. So that's kind of the main focus here. From this code perspective map, you can see Illinois is on the current code. Wisconsin should turn to dark blue on this map once they update this map. And those are the 2 states in the Midwest that are on this current code for energy. There are multiple compliance paths, as we discussed last week. You can throw the code book in the trash. You can just do ASHRAE 90.1 if you want to, but it's a one or the other, all or nothing thing. You can either do all of 90.1 or you can do all of IECC, but you can't pick and choose between them. You could also do IECC and do energy modeling. We're not going to talk about that today. So we're going to do number 2 on the screen here, which is prescriptive and mandatory requirements of the code. Like I said, some of these will be repeats from what we talked about last week. Economizers, code requirements. So if you guys don't know what economizers are, hopefully you do if you're on this webinar. But there's some ways you can explain those economizers. Dang, my luck is so horrible. So I switched to a different location with a different system, and I'm still getting a couple people typing in about audio issues. That helps out with. Interestingly, I went back and watched the recorded version from last week, and the audio was fine in that. So I'm not sure what's going on with some of the people that have issues here. We'll see. All right, an economizer. His job is to give you free cooling. Tom's saying there's no audio at all now. Hopefully there's a good audio connection for you guys. When explaining economizers to building owners. Okay, so there's no sound now at all, you guys are telling me, based on what you're typing in. 0 sound. No one can hear anything at all. All right. Sounds like it was out and now it's back in. Okay. All right, I don't know what to do about that. I switched everything, different computer, different location, different internet connection, different everything. So I'm not sure. When explaining economizers to consumers, to building owners, I usually explain it to them as free cooling in a way that they might relate to. So for example, at their house, if they're gonna have everybody over for Thanksgiving and it starts getting hot in their house, they're probably not turning their air conditioner on. They're probably gonna open up their windows. However, in a commercial building, most buildings, at least most modern buildings, don't have operable windows. And if they do have operable windows, it's not for all the rooms, it's only for the perimeter, right? So the way we handle that for the building owner is we open a window in their air handling system, in their air handler or their fan coil or their rooftop unit, something like that, to suck in that free cooling so they don't have to turn their compressor on. There are multiple ways that we can deal with that from a control standpoint. As you likely know, the three major ways we would use would be dry bulb temperature. Historically, we've set the economizer for a 55-degree set point. If it's below 55 degrees outside, we use the economizer. If it's above 55, we use the compression. The idea, the thought process there was if I can make 55-degree air from the outside air, that's probably what my DX system was designed to supply anyway, so I'm good, right? We can also look at enthalpy. Enthalpy allows us to look at both temperature and humidity simultaneously, if you will. So if the outside air temperature is low and the humidity is also low, we can go ahead and use the economizer to get free cooling. That allows us to push the set point for temperature up a little bit higher, right? I'll take 60-degree air if it's dry, but if it's 60 and raining, I probably don't want it. Then we have differential enthalpy, which is the best way from a control standpoint that we can control these things. So my supply fan can only get outside air, or only get air, if you will, from two places, the outside air duct or the return duct system. One of those two holes is going to suck air into the supply fan, or a combination of the two. If I want cooling, whichever airstream is cooler and drier, give me that one. So I don't care if the outside air is 80 degrees, that's fine. If the return air is 82, give me the outside air. It's better than the return air, right? My penmanship is fantastic. I'm well aware of that. All right, so that's kind of the deal with that. So from a code perspective, let me get back to my regular arrow. What's happening on my psychrometric chart is that if it's below 55 degrees, I'm going to get my free cooling. Right down here, I shouldn't have picked green. That was a bad color choice. John Madden would be so disappointed in my skill set right now. We'll do red, right? Below 55 degrees, give me free cooling. If it's above 55 degrees, give me compression. That's the historical way that we would have handled that, right? So what happens with the economizer? When do I have to do the economizer? So per IECC, an economizer is required when you have 54,000 BTUs or greater of cooling capacity. Basically 4.5 tons, you'd have to have an economizer. As you can see, there's a whole page of exceptions to that. Most of those exceptions do not apply to most of your projects. Some of them may, right? Number 3, if you got certain process things with humidity, fine, exception. Right? If you have, number 5, a church that barely has any operating hours, fine, you can get an exception. Number 8, if you got chilled beams or something, you could probably get an exception. But your normal school, retail, office, those kind of places, 5 tons and over, you're going to be using an economizer. That's per IECC. Wisconsin, if you guys from Wisconsin, there's an amendment to that. You still have to do the economizer when it's 54,000 BTUs and up. And additionally, all rooftop units have to have an economizer with no size limitation. So 4-ton, 3-ton, 2-ton rooftop unit would have to have an economizer. Split systems, 54,000 BTUs and up in Wisconsin. For economizer set point requirements, we look at the climate zone map, and this is consistent amongst the ASHRAE and IECC standard. It does change in the future going forward, but it isn't different right now for the codes that our states are using. So if you guys are in Illinois, you're climate zone 5A, because you're to the right of the moist dry line. And for you guys in southern Wisconsin, you are 6A. Most of you guys are in Milwaukee area and Chicago area that are on this call. So 5A and 6A. The good news is those are both the same requirement from the economizer standpoint, so we can talk about them simultaneously. If you have a dry bulb economizer, you're required to set up the control system to do the changeover at a 70-degree set point. You can no longer use 55. You can no longer use 60. It has to be set for 70 degrees. Paul types in a question, does this apply to new construction only? The answer is no. If you're interested, Paul, we did a webinar last week that went through all the details of the IECC. I can get you a link to that. or you can go to tecmongo.com/training and find it that way. It applies to everything: new construction, retrofit, renovation, alterations, everything, right? That's a whole nother webinar though. If you're going to do an enthalpy economizer, the requirement for all climate zones, including ours obviously, would be a set point of 28 BTUs per pound. Additionally, a temperature set point is 75. So you got to accept the outdoor air from 70 to 75 if you have enthalpy. You got to take that extra air, but you get to put limits on there from the humidity perspective. We'll graph that out. And then if you have differential enthalpy, where you're measuring both return and outside, then whichever one is lower is the one that you would take, up to a maximum of 75 degrees. So if we plot that out, instead of that black dotted line at 55 for our traditional set point for outside air changeover, the line moves over to the yellow area over there. Right? So what that essentially means is that this is an economizer day, this is a compression day, this is now also going to be an economizer day. Right? So I got to accept air that's 60, 65, 70 degrees outside air temperature as free cooling air. Now, you're probably smart enough to realize we can't cool the space with 69-degree air. However, 69-degree outside air is probably cooler than whatever our return air is. So it's an improvement from that. There are some problems, which is specifically right over here. Actually, let me clear that so you can see. Specifically up in the top there, there's an issue right here. That tends to become an issue. Sometimes you'll hear me jokingly call it the triangle of death. When I get up to these higher humidities, true humidities, not percentage, but real, actual, specific humidity, at these elevated temperatures, high 60s, I tend to have some issues there. So we'll need to resolve that. Otherwise, we're going to have problem jobs, which none of us obviously want. The way we resolve that is with enthalpy control. So if I have enthalpy control, what it allows me to do is draw this line here, this 28 BTU line. It's drawn in right there. And now this is my economizer days. This is compression days. Actually, that's not right. Bad job, Ryan, my little John Madden pen. This is economizer days. This is compression, compression, and also compression. The triangle of death leaves my plate. So the enthalpy control, while it is one more control widget to buy and install, it does help us significantly on making sure we don't have those relatively cool 68, 70-degree days that have high humidity, right? That's what helps us avoid that. In exchange for being able to eliminate that section, that triangle of death, I, on the flip side, have to accept all this air here between 70 and 75 that I would not have accepted on a dry bulb day. All right, so those are my choices. 70-degree dry bulb set point or 75-degree dry bulb set point and an enthalpy sensor set at 28 BTUs per pound. All right, so moving along with that. I should probably clear that. Additionally, an integrated economizer is required by code. So what that means is you have to be able to run the compression in conjunction with the economizer. Because if I'm going to make you take air that's between 55 and 70, it's not going to get the cooling done all on its own. So it's going to need assistance from the compression. So if you look at number 1 on the screen there in that section for integrated economizers, it'll tell you that the outside air damper has to go to 100% open whenever I got mechanical cooling also engaged, right? If I'm in an economizer day. Items number 2 and 3 we're going to talk about later because they don't really apply to the integrated economizer directly. I mean, they relate, but they're not. They really shouldn't be in that section as far as I'm concerned. So I'm going to shelve those for about 5 minutes. All right. So when we look at everything in conjunction together, blue down over here is a economizer day. Red is a compression day. The white area, that's going to be my integrated economizer day, where I could have the compressor on and also have when I have an outside air economizer, I also have to think about building pressure relief. I have to have a way for air to get out of the building. If I'm going to suck all this extra air in, it's got to leave somewhere else. On small, simple systems, that's typically done with a barometric relief damper. On larger systems, we typically do it with a power exhaust. So from the control guy's perspective, there'll be something extra to control there. The best way to control it would be based on building pressure. The inexpensive way to control it is based on outside air damper. It's not required that you can control the building pressure that way from a code perspective, but from a logic, from an engineering perspective, you should plan on that. Additionally, from a controls perspective, we need to have the ventilation damper close at night. Now, most You guys know the economizer has two jobs. One is free cooling. The other one typically is to bring the outside ventilation air that's required for IMC or Chicago code or Wisconsin code or ASHRAE 62.1, whatever you're following. There's a certain amount of outside air you have to bring in. We'll talk about that in a few minutes. But you only bring that outside air in during the occupied time. When the building is unoccupied, you're required by the energy code to shut off that outside air intake. A traditional simple system without DDC controls, for example, like a rooftop with a thermostat, those systems, whenever the fan turns on, the outside air damper goes to ventilation position. That's not allowed. We have to stop that from happening. So you either need to have a DDC system that limits that, or you need to have a thermostat that's smart enough to have an additional wire that runs up to the economizer to tell it to shut whenever the building's unoccupied, such as nighttime. That's required by the. You guys have seen this chart before, and you probably have heard me complain that a lot of economizers are not set up correctly, or they're screwed shut, or they're propped open, or the actuator's broke, or the linkages are broke, or whatever the case may be. There's numerous studies, including this one here, that points to, in this case, 64% of economizers are not functioning correctly out in the field. So because of that, the energy code, both IECC as well as Title 24, which kind of feeds into a lot of these codes, requires something called FDD, Fault Detection and Diagnostics. We did talk about that last week as well, which is kind of a little bit of a repeat for the controls guys this week. That is required by code. There are numerous things that your economizer controller, whether it's a DDC controller or whether it's a Jade or a Belimo Zip or whatever it is, there's numerous things on the list here that your controller has to babysit. Make sure you don't have excess outside air, excess return air, make sure your temperature sensors are not all out of whack, things like that. So it's babysitting itself per the spec here in the code, and then it has to report those alarms back to the building automation system. The economizer controller shall be capable of reporting faults to a fault management application. That's basically your building automation system. That's accessible by day-to-day operating or service personnel. So it can't just be on the screen. In this case, the Jade controller in the corner, it can't just be on the screen up inside the rooftop. That's not accessible to day-to-day people. It's got to be pushed back down to your building automation system where it can be displayed on the computer monitor or emailed to the building guy or texted to the service provider or something like that. If you don't have a BAS, then your alternative is to display the alarm on the thermostat itself. But you need to have that FDD monitoring, and you need to report it down into the space to either the building managers or the occupants in some way. That's kind of a big change from previous codes, kind of a unique thing. For an energy saving standpoint, I just threw this in a tool here that we use quite a bit. If you want more information on this energy modeling quickie tool, it's a 5-minute type tool. Let me know. I'll give you a webinar link that's specifically on how to use this. But from today's perspective, I have 3 units I'm comparing. I have the first one, the baseline, which is a entry-level, basic, everyday unit, like the lowest efficiency thing that anybody manufactures right now. The middle choice there is a energy code compliant unit, something that meets the IEER requirements we talked about last week from an energy perspective. And the third unit is a code compliant unit with an economizer also installed on it. Everything else is identical on these units. The tonnage, the size, the horsepower of the fan, the heating efficiency, everything else is identical. Only those things are different. So if you look at the energy savings, going from an entry-level unit to a code-compliant unit saves me 1%, or in the case of this example, on a 10-ton unit, saved me $27 a year. If I put the economizer on, it saves me 7%. So the economizer is getting me quite a bit of energy savings above and beyond what just having an efficient unit might. All right, we got our first quiz question. As a repeat, this is especially important for you guys that need PDH credits. You need to get 4 of the 6 questions correct in order to get PDH credits. I will also mention, because this happened last week, each person that's registered would have to answer the questions themselves. If there's 7 of you guys sitting in a room and one of you is answering, whoever's logged in is going to get the certificate. The other 6 are not going to get it. Right? Just that came up twice last week. Even though it specifically says it in the registrations, I know everybody doesn't read the details. I get it. All right, question number 1. Which is the current statewide code of Illinois and Wisconsin? Your choices are ASHRAE 90.1 2010, 90.1 2016, IECC 2015, IECC 2016, or IECC 2018. Which one is the statewide code based on for both Illinois and Wisconsin? I'm going to look and see if any other questions came up while you, Stephen, I see you wrote into the question box your answer. You need to actually click on the question that populated on the screen in order for it to go into the database for your scores to get graded later. And Stephen, your answer was not correct, so don't pick the one that you just typed in. A little freebie tip there. Looks like nobody else typed in questions for me, and 90% of you answered the question, so I'm going to close the quiz in 5, 4, 3, 2, 1. And looks like 88% of you got it correct. You had said IECC 2015. That is the correct answer. All right, what else is required from a control perspective? I said we're going to come back to that integrated economizer section of the IECC 2015, and here we are back at that section. We talked about number 1. Now number 2 and number 3 come into play. Number 2 basically says that if you're going to have more than 75,000 BTUs of cooling, you must have at least 2 stages of mechanical cooling. And read up at the top, hot gas bypass is not really considered a stage. You kind of need 2 compressors, or I guess 1 compressor with 2 stages, or a variable speed compressor, or digital scroll, or something like that. So keep that in mind, that if you have those size units, you're going to need to be able to have multiple stages. Then, more interestingly, from the controls guide perspective, number 3, other DX units, including those that control space temperature by modulating airflow to the space, shall be per the table below, right? Modulating airflow to the space to control space temperature. That would be a VAV system, or a VVT system, or some other type of, air-based, a damper-based zoning system. The thermostat controls the airflow damper, right? Space temperature to control airflow. Or using airflow to control space temperature rather. So in those cases, VAV or VVT or any other airside zoning system, Honeywell's 3-zone panel, whatever it is, you're going to need to have either 2, 3, or 4 stages based on the tonnage. So once you get to 65,000 BTUs, which is that 5.5 tons, right? You need 3 stages of cooling if you have zoning. And then once you get up to 240,000, which would be 10 tons, 20 tons, and you need 4 stages of cooling, right? So 20 tons and up, you need 4 stages of cooling. So from a controls perspective, you're going to have to plan on how you're going to control 2, 3, or 4 stages in conjunction with your zone damper system. Kyle types in a question, are we going to go over T-stat options? Some do FDD, but some do not. Some do occupancy, and some do not. We covered that last week in the webinar, so I'll refer folks back to that, Kyle. If anybody needs a list of thermostats that comply with IECC 2015 and all of the codes related to that, let me know and I'll give you that list. It's a very short list of thermostats that comply with everything related to the code. And most manufacturers that say they're FDD compliant are, but they don't do the other things that the code requires. All right, in addition to the multiple stages, you may also have to have multiple fan speeds. You may have to control those as well. So we talked about this last week too, and this is one of the last few things that repeat from last week, and then we'll be on to all new stuff. This section, 403.4.1.1 fan airflow control, is unfortunately accidentally stuck under the hydronic and multi-zone HVAC systems. That gets corrected in the IECC 2018, and it gets its own section. But for 2015, which is what we're doing right now, it is under that section, so hence it only applies to hydronic systems or multiple zone systems. So once again, if you have VVT, VAV, Honeywell zoning panels, or any other type of airside zoning system, once you get above 65,000 BTUs on your DX system, you are going to have to include multiple stages of fan operation, at least 2 stages. Now you can go full variable if you want, that's fine. But you have to have at least 2 stages of fan speed once you have zone dampers on there. If you don't have DX and you have chilled water systems, then instead of based on BTUs, it's based on fan horsepower. Once you get to 5 horsepower and up, you'd have to have at least 2 stages of fan speed for chilled water. And then if you have evap cooling, which is very rare, then it's a much smaller amount as well. Demand control ventilation is frequently required by code as well. In Illinois, if the space has a people density of 25 people per 1,000 square feet or greater, and in Wisconsin, if it's 40 people per 1,000 square foot or greater, then you're going to need to consider demand control ventilation, which is where we use a CO2 sensor to monitor the breathing activity of the building occupants. And the more breathing activity, the more people, and hence the more people, the higher the ventilation we need. Or more importantly, the less people, the lower the ventilation air we can go down. Right? So this is when that code would kick in. There's a few exceptions to that. If you got small systems, you don't have to do it. If you have a zone dampered system with pneumatic controls, that'd be exception number 2 there. You would not have to do it, right? But if you have a constant volume system or you have DDC VAV, then you would be in the category of having to do demand ventilation on these high density type spaces. Typically, it's conference rooms, meeting rooms, movie theaters, things like that. We got a lot of people in a relatively small space. If we look at that same software tool and we add a 4th column for a code compliant unit with an economizer and DCV, just for argument's sake, then that gives us, instead of 7% just for the economizer, it gives up to 13% for the economizer with the DCV. So there is some real energy savings for a fairly inexpensive sensor. For my friends in Wisconsin, your energy savings will be less than I'm showing on the screen, because in Wisconsin you already have the lowest ventilation rates of anywhere that I'm aware of in the entire country. So your savings potential will be less. For folks in the city of Chicago, you have the highest ventilation rates that I've ever seen. So your savings potential will probably be higher than we're showing on this chart here. David typed in a question. I'm going to go back because it's a good question. David typed in a question down here. How does Aeroside fan control affect typical bypass damper use for aerostatic control? So I'm assuming David's talking about a constant volume zoning system such as DVT or a Honeywell zoning damper system. We have a bypass as zone dampers throttle back. The bypass opens to relieve pressure. You would still use the bypass damper if you were going to use a 2-speed fan operation. The fan would stage itself down based on how many stages of cooling we're running. So when we drop down to stage 1 of cooling, from stage 2 down to stage 1, the fan would go down to 2/3 of its fan speed, which just means your bypass damper would open less. That's all, because the fan would be providing less CFM. However, if you choose to do your fan control with a full variable speed fan instead of a 2-speed fan, then you would be eliminating the bypass damper, because the bypass damper and the variable speed fan would then both be controlled based on duct static pressure, and hence they would fight each other. So if you have full variable speed fan, it'd be more like a VAV type system and you would not have the bypass. If you have a 2-stage fan, it'd be more like a VVT type system and you would still have the bypass. It would just do less work on low load moments. Parking garages. There are some control requirements there as well. For parking garages, we'd be using CO sensors instead of CO2 like we use for people. Right? CO, carbon monoxide, byproduct of vehicles. CO2, carbon dioxide, byproduct of people. We would need to use sensors like that in the parking garage per the energy code to throttle back the ventilation rates when there are no or less vehicles in the space. So keep that in mind. Now, it's for bigger parking garages. It's got to be garages that have a total exhaust of 22,000 CFM. So it's not going to be somebody with a condo with 3-4 car garage or something like that. This is a big parking garage from like downtown Milwaukee or downtown Chicago kind of thing. All right, quiz question number 2 for you guys playing along at home. All dry bulb economizers in climate zones 5A, which is northern Illinois, Chicago area, and 6A, southern Wisconsin, are required to have which of the following? Choices are I'm going to read them first, otherwise you guys answer the wrong things because you don't listen. A, occupancy interlock, fault detection, and CO2. B, occupancy interlock, fault detection, and a 70-degree outside air changeover set point. C, fault detection and CO2. D, DDC controls. Which of these are required for dry bulb economizers in northern Illinois and southern Wisconsin? anybody has any further questions for me, you can type them in the question chat box and I'll do my best to answer them. Right now, 52% of you guys have answered the quiz question, so I'll give it another 10-15 seconds for you guys to finish processing all the options there. Most of you guys are getting it right. Which I guess doesn't help you. It just only makes you feel bad if you got it wrong, I guess. All right, I'm going to close the quiz in 5, 4, 3, 2, 1. All right, the correct answer is B. Occupancy interlock, fault detection, and a 70-degree outside air changeover set point. All right, moving along. Other mandatory rules in the IECC 2015. Before we get off the energy code and move to other codes, let's finish up this guy here. There are some key things for controls and then some very specific things for VAV, and then we'll move into the other codes. So thermostats and controllers must be 7-day programmable. That's not hard to do. Got to have setbacks initially set for 55 and 85. That's not hard to do. Personally, I like 60 and 80, but the code says 55 and 85. Got to have at least a 5-degree deadband. That means there must be a minimum of 5 degrees enforced between the heating and cooling set points at all times. So if your cooling set point is 75, your heating can be no higher than 70, right? You can't have 70 for heat and 72 for cooling. That would not be allowed. 5-degree deadband between the heating and cooling. It's got to maintain power, or schedule on power loss. You cannot have overlapping heating and cooling set points, sometimes referred to as inverted set points. That is not permitted. You got to have some way for the occupants to override the thermostat in a normal fashion, as opposed to using paper clips and jamming them into the lockbox. They got to have some kind of normal method, either with an occupancy sensor or an override button. You have to have an adaptive intelligent recovery type routine or optimal start, whatever you want to call it. That's where the stat system starts enabling heating and cooling function prior to the occupied time, so the system ends up at the occupied set points at the same time the schedule was supposed to begin. The way that saves energy is instead of setting a system to turn on at 6 a.m. to get to set point by 8 a.m., you actually program it to start at 8 a.m. And some days it may have to start at 6, but in most days it's going to start at 7:15, 7:22, 7:41, and all those little half an hour, 45-minute savings, if you will, add up over the course of the year, which is why it's code required. It's super easy to do on any DDC system. It's also readily available on most higher-end programs. You have to have an interlock between the thermostat or the DDC system to the ventilation system. I guess technically you don't have to have a thermostat, but you could have a second device on the wall next to the thermostat, but that would be kind of silly. Just get a thermostat that has an extra output that does all this for you. But the ventilation damper needs to remain closed until the occupied period begins. Like I said, if the schedule begins at 8 a.m., you leave the damper shut until 8 a.m. Even though you may want to turn heating and cooling on earlier than that to start warming up the building, you leave the damper shut while you're doing the warm-up period or cool-down period, whichever you may need. In regards to controls, low leak outside air shutoff and exhaust air dampers are required, and they're required to be motorized. If the building's above 2 stories, all those dampers have to be motorized. So from a control standpoint, you need to plan on controlling that. If there's a damper on your exhaust system, it needs to have a motor on it. It cannot be barometric unless it's a short building, less than 2 stories, or it's a really small fan, less than 300 CFM. Economizers dampers always need to have this interlock system. There are requirements in the code for boiler outside air reset. The code does not tell you what the reset schedule needs to be. I guess you could reset it from 170 to 180 supply water if you really want to. That's pretty lame, right? You probably really want to go from 150 to 180 on a traditional system, and it'd be 120 to 180 on a condensing system. But from a code perspective, you just have to have outside air reset controls installed and operating on the boiler plant. The set points are up to the designer and if you have snow melt systems, there are 3 minimum requirements you must install from a control standpoint. You have to have a precipitation sensor, a moisture sensor, right? If there's no moisture outside, you shouldn't have a snow melt system on, right? So only if there's moisture outside. Typically, those are sensors that are mounted either in the concrete, or if you forget to do that during concrete installation, you can get one that goes out like the grass area. but they have a little grid on top of them with a little electric wire on there. And if there's moisture on the grid, it completes the electric circuit and hence tells you that you have a wet sensor or not. You need a precipitation sensor. You also have to measure the pavement temperature. If it's above 50 degrees, you have to cut off the snow melt because that means it's not snowing. It means it's raining, right? If there's moisture and it's above 50, it's not snow or ice. And then you also have an outside air temperature cutoff at 40 degrees. So if it's above 40 degrees temperature, 50 degrees pavement, and no precipitation, any one of those three, you're disabling your snow melt. If you have freeze protection systems, right, for like piping and stuff like that, like heat trace tape wrapped around piping, those cannot be running wild. They have to be controlled, and they have to be controlled to a specific set point of 40 degrees for normal fluids like water. If you have other fluids, then you can pick a different temperature, but you have to pick one that's appropriate, meaning 5, 7, 8 degrees above whatever the freezing point is for that fluid that you're concerned with. If you're going to do heating outdoors, for one, the heating must be radiant. That's the only type of outdoor heating allowed. It means radiant tubing in the concrete or an infrared heater overhead. Those would be allowed types of systems. Additionally, those systems have to be in an occupancy sensor, like a motion type sensor. You can't just have those turned on a switch because people put them on a switch, they turn them on, they forget them being on, and they forget to turn them off for several days. They got to be in an occupancy sensor, so you need that type of control with you. For ERVs, if you have an ERV system, which is sometimes required by code, but even if you put an ERV in, not required by code, you just want to put one in, that's fine. But as soon as you put an ERV in, you have to have bypass dampers on the ERV. And those bypass dampers act like an economizer. You use the typical economizer settings, if you will, the 70 degrees, the enthalpy setting, all that kind of stuff, to determine if free cooling is available. And if it is, you shut off your ERV. And then whether you have a wheel or plates or whatever, you open up the bypass dampers to bypass the air around the ERV so you're not paying for the extra static pressure drop penalty. You do not want to operate an ERV on an economizer situation because it's actually going to recover energy from the space, which is going to be detrimental to what you're trying to do. So you need to disable the ERV and provide an economizer function using bypass dampers. All right, hydronic control systems, boiler and chiller type plants. There are specific controls you have to have on some of these. I mentioned the outside air reset already. Same thing on the chiller systems. You have to do the same kind of thing. You cannot provide the same chilled water temperature all the time. You have to have something that changes the chilled water temperature. And they give you some options in the code. You can do it based on zone valve positions. If none of your zone valves are 100% open, that obviously means they're all being overserved. So you should be able to reduce it, right? Based on return water temperature, you can do it based on outdoor air temperature, or whatever schemes you want to come up with. But the chilled water and boiler water temperature have to be reset. If you have hydronic systems that have 10 horsepower pumps or larger, they have to have variable flow. They got to have a VFD on them, essentially. Or if they're small enough that you can get one, you can get an ECM motor on there that's variable speed. Either way, but they have to have variable flow if they're 10 horsepower and greater. You have to have isolation valves if you have more than one chiller or more than one boiler. That means if you're only running one of your chillers, you can only flow water through one of the chillers. The other chiller in parallel has to have valves that shut off to prevent flow from going through them and paying that extra pressure drop and that extra mixing. Now, if you have two chillers in series, there's an exception for that. You can flow water through both of them if they're in series. But if they're in parallel and you only need one running, you shut off the other one and isolate it with valves. And that has to be an automated control system. If you have two-pipe systems, which I'd highly recommend you avoid, but some buildings already have them, so you're retrofitting them, so it is what it is. Sometimes you'll see these in mid-rise and high-rise condos that have chill water and hot water. And the condo, they kind of figure out there's not a lot of cooling load compared to a commercial building. Maybe we can get away with it. People complain in the spring and fall for a couple weeks, and then they forget about it, right? Well, if you got a two-pipe changeover system, you have to have a dead band of 15 degrees outdoor air temperature between them. For example, you can run the boiler up to, say, 60 degrees and run the chiller down to 75, but between 60 and 75, you can neither run the chiller nor the boiler. They would both need to be off, right? You got to have that dead band on there. You're doing neither one of those things. You have to have a minimum wait time before you change over. You have to have a minimum temperature before you change over between the two. Because we don't want to have a system that's been heated up with the boiler and then immediately cut over the chiller. It's very wasteful. Right? So they have those kind of limitations. Cooling towers, if you have 7.5 horsepower or larger, you have to have a way to reduce the fan speed. So that could be a VFD. I guess it could be a bunch of little tiny fans and stage them. You can do it that way, I suppose. But you have to have some way to control that airflow and reduce it down. You can control it by leaving water temperature if you want to. However, normally we, Carrier distributor, we recommend that you do it based on the output of our chiller, which would be related to the condenser. We have an output on there specifically for head pressure control to send that over to the cooling tower to reduce the fan speed. You have a water source heat pump loop, which is fairly common in downtown Chicago and even in Milwaukee. You have that. You have to have a deadband also. So it's a little bit different than the two-pipe system, but you have a deadband of 20 degrees in this case between the boiler and the tower operation. So that means if I have the boiler running up to, say, 58 degrees, I run the boiler up to. That means I can run the cooling tower when it's above 78. But when it's between 58 and 78, I can neither put the boiler on or the tower. I have to have that deadband on my control sequence between those two. All right, so that kind of stuff there. Let's do quiz question number 3 and get us back on schedule here. Number 3, which of the following is not required on all, so let me be really clear, because I just got messed people up before. Which of the following is not required on all zoning systems with DX equipment 5 tons and up? Not all being the very key words here. So 3 stages of compression, economizer, 2-speed supply fans, outdoor air reset, or both A and C. Which of these is not required on all systems? Not in all keywords. All right, let me see if there's any other questions typed in yet. There's not, so we're doing okay. You guys are killing me with the answers. Almost everyone's getting it wrong. Which of the following are not required on all DX systems? All right, I'm going to close it in 5, 4, 3, 2, 1. All right, so most of you got the answer correct. I should say most of you. The highest correct answer was correct, which is outside air reset. That is not required by code. If you have a zoning system for that size and up, 3 stages of compression is required, an economizer is required, a 2-speed fan is required. Outside air reset is not required. So not as many people got that right as I thought should have. So obviously I worded it in a confusing way, even though I stressed the not and the all. All right, keep on moving here. Quiz question number 4. Which of the following are not mentioned in the IECC 2015 code? Not mentioned. A, economizer. B, snow melt controls. C, variable frequency drives. D, duct smoke detectors. Or E, all of the above. Which are not in the IECC in any way whatsoever. All right, I'm going to close it in 5, 4, 3, 2, 1. And you guys redeemed yourself. 96% of you got that correct, which is duct smoke detectors are not part of the energy code. All right, VAV controls in the energy code. There's some very specific things, and some of these are different than the 2012 code. So there are some changes here, and there's also some things that are the same. I'm just going to stress some of those again because a lot of people weren't following them properly. This one is a change. This is a new one, static pressure sensor location. Historically, on the VAV system, we have put the duct static pressure sensor 2/3 down the duct, just because we were told to do that. No real science behind it, just kind of a good average guess, right? An art, if you will. Ideally, we would have measured static pressure drop at every single VAV box and controlled the worst one, but no one's going to buy all those controls. So we put it 2/3 down the duct and called it a day. That's no longer allowed. Now we need to put the static pressure sensor wherever it needs to go on the duct in order for us to have a set point of 1.2 inches of static, right? So wherever that ends up being, if it ends up being 2/3, great. If it ends up being halfway down the duct, if it ends up being 9/10 down the duct, wherever it is, that results in a 1.2 inch static set point. I don't know who chose the 1.2. I don't know why we had to pick that number. 1.5 sounds nice and round to me, but whatever. That's the number that they had picked. In some cases, this may mean you do multiple sensors if that's so far down the branch that the ductwork's already split. You also have to do static pressure reset. This is not new. This was required in the previous version as well. That means that I have to look at all of my DDC controlled VAV boxes, and if nobody's 100% open, obviously I'm giving them too much airflow, so I need to start reducing the static pressure down. Right? So instead of giving them 1.2, I'll give them 1.1 and see what happens. I'll give them 1.0 and see what happens. And then when somebody finally opens up near 100%, then I would start opening it or raising the static pressure back up again. That's fairly easy to do with DDC controls. It's fairly standard. You do need to tell your DDC programmer that you want that, but it shouldn't be anything hard for them to do. They've all done it before. Just ask for it, specify it. If you don't have DDC controls, then you do not have to do this routine because it's impossible to do. Not impossible, but it's freakishly complex to do on a pneumatic system. Talk about these two together. If you have small horsepower fans on your fan coils and series fan powered boxes, you need to control them with an ECM. All series fan powered VAV boxes are required to have an ECM, electrically commutated motor. That is a requirement on there. So keep that in mind. If you have VAV controls, you also have to do supply air reset control. So not only are you resetting static pressure for VAV, you also have to reset supply air temperature. Typically, you got to reset this from 55 to 60, right? Because it says 25% of the difference between the design supply air temperature and the room air temperature. And in a 75-degree room with a 55-degree supply air design, that means 5 degrees of reset. So you're resetting from 55 up to 60 degrees. You typically reset that based on the average zone temperature as compared to the average cooling set point for those zones. So if on average the zones are all pretty happy, if you will, or overcooled, if you want to think of it that way, we start tweaking the supply air set point up from 55 to 56 to 58 to whatever it needs to be. So that is a requirement of the code as well. That is required on both DDC and non-DDC systems. So if you have non-DDC, you're probably going to do it based on outdoor air temperature. If you have DDC, you're going to do it based on indoor zone temperature. But you do have to have both supply air reset and static pressure reset. This comes up as well in the code. It's not new in the code, but it's not dealt with properly sometimes. Generally speaking, you're not allowed to reheat air that you've already previously cooled on it per the. However, VAV systems have an exception. If they throttle the VAV damper back down to 30% of the supply CFM, you are then allowed to have a reheat coil, meaning hydronic coil or electric reheat or one of those types of things. So you are allowed to do it if you have VAV. You cannot do constant volume reheat. That is not allowed. But VAV reheat is allowed if you follow the rules listed here. All right, other codes that come into play with the control systems. ASHRAE 62.1, which is the IAQ standard, very closely associated with the International Mechanical Code. And for today's purposes, in this discussion, we can talk about them interchangeably. For these perspectives, these guys are both requiring how much outside air is required for us to bring in by code. Right? And this does relate to our control systems. So from a controls perspective, this is what the language would state. You have to have controls that manually or automatically maintain the outside air intake to the prescribed levels, which I'll show you here in a second. Systems with supply fans that are variable speed, either single zone VAV, which is staged air volume, or multiple zone VAV, which is a traditional VAV system, shall provide one or more of the following things listed there. So the normal way to do that would be to have two dampers, outside air and return air, modulating to maintain the outside air intake. The reason they reference it this way in relation to the supply fans and the staging is because if I put in a 2-speed fan and I slow it down to the lower speed, it's going to inadvertently reduce my outside air intake CFM. So if I have a 2-speed fan, I then have 2 minimum positions for ventilation that I have to maintain. One if my fan is on 100%, the other if my fan is on 67%. So a traditional economizer controller would not be able to do that. You would need DDC controls, or if you had a simple thermostat system, you would need a JADE-type economizer controller with dual minimum ventilation positions. How much ventilation air do you have to bring in? Right, here's the formula for that. The formula makes it sound scary, so I'm going to skip the formula and show you the table, which makes it look slightly less scary. I need, in this case of an office building that I have highlighted, I need 5 CFM per person plus 0.06 CFM per square foot. ASHRAE 62 and IMC both do it this way, a per person and a per square foot number, and you add them together. They've been doing it that way for over 10 years. The reason we do it that way is because when we get to demand ventilation, we have to be able to separate those two components. So therefore, from a code perspective, we have to tell you what the two components are instead of having them in a blended number. So you simply add them together, right? If I have a 100-person space, 100 times 5, that's 500 people. If I have 10,000 square feet, 10,000 times 0.06 is 600 CFM. 500 CFM plus 600 CFM means I have 1,100 CFM of outside air required, right? You guys are in Chicago, it works completely different. Chicago, the city of Chicago and the state of Wisconsin are different from like everywhere else. Everybody else that I know of does this. And there's like 4 pages of tables like this for different spaces. Chicago and Wisconsin are different. Wisconsin is simpler. Wisconsin just does 7.5 CFM per person. There's no square footage discussion. There's no 5 CFM, 10, 15. It's always 7.5 for all building types. It ends up being significantly lower than anything that's in these tables up here. Right? But that's how Wisconsin would do it. Chicago tells you not how much outside air to bring in. They tell you how much supply air to bring into the space, which is completely crazy to me because supply air should be dictated by the load. But they tell you how much supply air to bring into space. In this case, 0.6 CFM per square foot for an office. Then they tell you additionally that 1/3 of that needs to come from outside. Right? So in this case, 0.2 CFM per square foot from the outdoor. Very complicated way to do it. If you do work in the city of Chicago, it seems normal to you because you've been doing it for 100 years and it's fine. But if you're from outside, you're like, what? CO2 is allowed by ASHRAE 62 and IMC, so it's sometimes required by IECC and required by 90.1. On the flip side, it's allowed by 62.1 and allowed by IMC, which makes sense because those codes need to be synced with each other. That's just the language showing you that CO2 is an acceptable means to reduce the ventilation rate below the otherwise code prescribed minimum. So you can go below the 1100 in my previous example, right? That example there, I can go below that. I modulate the people portion. I do not modulate the square foot portion, which is why these numbers got split. So I had 500 for the people in my example, and I had 600 for the square footage in my example. I would then modulate the outside ventilation rate between 600 and 1100. The city of Chicago does it a little bit differently, as you would expect. Their CO2 requirements have a fixed set point of 1,000 parts per million. Whereas in other places, we typically do 700 above the outdoor air level. So if it was 450 where you live, it would be an 1,150 set point. But the city of Chicago does not do it that way. They have a flat number of 1,000 parts per million, which is typically less aggressive than other places. But when Chicago set that 15 years ago, it was before ASHRAE had set any standard for it. So Chicago's kind of going out on a limb on their own there. Paul asked the question, did I say Wisconsin was 7.5 CFM per person or square foot? It's 7.5 CFM per person in the state of Wisconsin for ventilation code for an office building, or almost all spaces for that matter. There's very few exceptions to that. If you guys are doing LEED projects, CO2 does tie into that discussion as well. For densely occupied spaces, if you want to get a specific credit, you have to do outside air airflow monitoring on the main, and then CO2 monitoring in the spaces that are densely occupied. So there's another tie in there. I know LEED's not really a code, it's more of a standard, but we kind of threw it in there. All right, question number 5 for the quizzes. Carbon dioxide CO2 sensors for demand control ventilation are required or allowed by which of the following codes and standards? Which of these require them or allow CO2? While you guys are answering, I got a question from Mohammed. If we can send a copy of the slides. Usually I say yes to that question, except for when I do presentations like this. All of these codes and standards that I'm showing you the language of, and it's a lot of cut and paste out of the code book, as you can see, those are all copyright protected, and I have gotten, I don't want to say in trouble, but we'll say warned about sharing those in the past. So I'm not going to share slides that have a bunch of reproduced work from others on there. However, no one seems to have an issue with me using the code book information for training purposes. So there is a link that'll be available for you to rewatch this webinar if you want. But actually giving everybody the code book cut and pasted one page at a time, I can't do that. All right, I'm closing the question in 5, 4, 3, 2, 1. Correct answer is E, all of the above. 82% of you guys got that correct, so good there. All right, ASHRAE 15, which is a refrigerant standard. There are some things that come up on control systems in that regard. I know I got ASHRAE 15 2010 up on the screen, but newer versions of it, as it relates to this particular discussion, are in fact the same. So if you have a chiller room, or I guess any other room with refrigeration equipment in it like that, for example, if you had like a supermarket with a bunch of compressors and stuff in there, right? But in this case, a chiller room, I need to have the ability to monitor refrigerant for leak potential. I have a very large quantity of refrigerant in a fairly small room, so I have to have sensors in there to detect if refrigerant leaks. Additionally, the alarm shall enunciate both visual and audible alarms inside the room and outside every entrance to the room, right? So what does that look like for an actual project, if you will? Oh, I should also mention Chicago is in sync with that. Audible alarms will be placed directly outside the room. Visual alarm shall be consistent with flashing yellow light, etc., etc. So same kind of basic idea. The threshold amounts, depending on the refrigerant you have, right? So I have a couple different amounts on here. For most refrigerants in a chiller room, 134A, R22, R11, R12, all of those guys. If I get to 250 parts per million, I need to generate an alarm, right? And that alerts the people that are in the space or people that would accidentally go into the space, hey, stay the heck out of here. Other refrigerants have different alarm points. I know some chillers are 123. I don't know why you buy those ones, but if you did, those have a lower alarm point because the refrigerant is a little bit more hazardous. So their occupant threshold is 12 parts per million. All these refrigerant sensors need to be mounted down near the floor because generally speaking, refrigerant is heavier than air, so it'll accumulate and pool down by the floor. So typically mount them 1 foot above the floor. Each sensor, for most manufacturers, handles about a 20-foot radius of detection, which for the most part means 1 sensor per chiller. I guess if you had 2 chillers right next to each other, you could stick 1 sensor between them. That does happen in some cases, as long as they're the same refrigerant. But generally speaking, it's a 1-to-1 relationship. We take a typical chiller room, we laid it out here, right? So I have 4 different chillers in here. 3 of them are one refrigerant, 1 is the other. In this case, we chose to put a sensor by every single chiller. We could have Probably this sensor right here. Probably could have covered this chiller and that chiller if we really wanted it to, but we put one by each just because. It's not that big of a cost difference in the grand scheme of things. Additionally, we have to have some kind of visual and audible alarm inside the room and then outside each door to the room. So in this case, I have 2 entrances, so I need to buy 3 alarming panels for the same system. 1 inside, 2 outside. I could also have 1 main one on the inside and 2 secondary panels that are just feeding off the main one. That would be fine also. But I have to enunciate it outside every door, and I have to enunciate it inside the room. All right. All right, a couple other things just quick bullet points as we wrap up on our last slide here. And we do have one more quiz question as well. ASHRAE 62.1 and the ASHRAE handbook both specify a maximum for overhead heating systems. So think of an office building with a rooftop, if you will. Overhead heating systems, no more than 15 degrees supply air above the space temperature. So if the space temperature was 75 degrees, your maximum heating supply temperature is 90. Your space temperature is 72. Your maximum supply temperature is 87. If you don't do that, ASHRAE 62.1 will kick in extra rules for your ventilation effectiveness, which will actually end up requiring you 25% more outside air CFM than you otherwise would have had to do. All right. So keep that one in mind. That one's pretty easy to comply with. But if you're doing a rooftop system, there's tons of rooftop systems that are out there way above 90 degrees. I see a lot of VAV boxes trying to maintain above 90 degrees. That's way, way too high. That means you're heating the space above 75, which doesn't make sense. If you heat the air too much, it cools up at the ceiling, as you might guess, and then the ventilation air does not end up going down into the space. So you have both a comfort problem and a ventilation problem. ASHRAE 62.1, which is the IAQ standard, also specifies a maximum of 65% relative humidity in the space. ASHRAE 55, which is the thermal comfort standard for humans, specifies 60%. So I end up controlling the cooling system to maintain below 60% because that satisfies both requirements. If you have a VAV system, this is not hard to do because you have lots of compression stages. If you have chilled water, this is not hard to do. If you have constant volume systems and you only have 1 or 2 stages of DX, this becomes very hard to do on low load days. So not oversizing your system is step number 1 on that. But from a control standpoint, it's kind of late. So at that point, you're really kind of struggling on the control side what to do. You can slow fan speed down. You can add an ERV. You could control humidity on demand as opposed to just temperature only. So those kind of things. There is no lower limit from any of the ASHRAE standards for relative humidity. Only upper limits, no lower limits. There used to be a lower limit of 30%. That got eliminated over 10 years ago. I don't remember why, but there's no lower threshold. For you controls guys doing City of Chicago work, whenever you have a plenum ceiling, they're going to make you put everything in conduit. You probably already know that, but it doesn't matter if it's 1 volt, DC wire, they still want it in conduit. Ethernet cable, conduit, right? 24 volt AC wire, conduit. Everything goes in conduit in the city of Chicago. It's the only place I know of in the country like that makes you put all the low voltage wiring in the plenum in conduit. You also cannot have open actuators because they have control wiring on them. On the shaft, you have to put them in a control enclosure as well on the VAV boxes. Duct smoke detectors, our last topic here. Whenever you have a 2000 CFM system or larger, chances are very high you need a duct smoke detector. Almost every code requires it. International Mechanical Code and pretty much all of the local codes that piggyback off of that would require it. IMC requires it in the return duct when it's above 2000 CFM. If you are following NFPA, National Fire Protection Association, then it's required in the supply duct. If your municipality is following both NFPA and IMC, then you'd have to put 2 duct detectors in, 1 on the supply and 1 on the return. And then for both of those codes, either one, if you're following either code, if you get to 15,000 CFM, you always require a supply and a return duct smoke detector. Sometimes these are provided by the controls guy, sometimes the mechanical, sometimes the electrical, but someone's got to provide them and wire them up. And then obviously they're wired to shut down the supply fans in the case of duct smoke detection so we don't spread the smoke around. All right, our final question, we're wrapped up here. A chiller room with 2 entry doors will require how many audible visual alarm stations? 2 entry doors, how many alarm stations for visual and audible do you need? Just to be clear, one station does both visual and audible. Right? Don't take your number and double it. You got a room with 2 doors. How many visual alarms, how many light bulbs do you need total? Like 84% of you have answered. So I'm going to give it 5, 4, 3, 2, 1. Closing it. And 66% of you got it correct. You would require 3. 1 inside the room and one outside each of the 2 doors, right? That would get you the total of 3. If you guys need more help on any of this stuff, last week we did a webinar on IECC 2015 in general, both residential and commercial. That is available on our website if you want to go watch the recorded version of it. This one we just did right now will eventually be up there as well. And then next week we have another webinar specifically related to energy code and some of the challenges with complying with rooftops, such as the thermostat thing that Kyle had mentioned in his question earlier. So with that, we are all wrapped up. I thank you guys for attending. I'll stick on for another minute or two and see if any more questions get typed in. Well, looks like we don't have any more questions, so that either means I bored you or I'm perfect. One of the two. Either way, I'm good with it. See you guys next week. Thanks. Bye.